Alright, so we are talking about mirrors and lenses. This is week 27, part 1. So let's talk about law of reflection. So what this says is theta sub I equals theta sub R. So this is talking about, here we have a mirror and a light ray comes in and then it bounces off of it. And that's probably pretty straightforward to you. You're familiar with mirrors and you can guess that this angle here, which we call theta I for angle of incidence, and then this over here, theta R for angle of reflection. You can imagine that those two are equal. So in words, it says angle of incidence, that's when it hits, incidence, I think this is how we spell it, equals angle of reflection. Whoa. Reflection. Alright. Your image in a plane mirror. So I think we saw this previously, but you should definitely know what happens. So sort of a dashed line right by your eyeballs, okay, and so the top of your head, light bounces off the top of your head, off the mirror, and oops, and goes back to your eyes. So it would be more like this, halfway in between, and then there, and then there. And light from your shoes goes like this, bounces off your shoes, bounces off the mirror, heads to your eyes. And so what happens is your eyes perceive the light as having come from over here. And your eyes perceive the light bouncing off the top of your head as having come from over here. So, when you see your reflection, this is actually what we call a virtual image. There aren't actually light rays crossing there. It is simply your brain perceiving, because your eyes see light coming from this direction, even though it came from this direction, your brain doesn't register that. Your brain registers the light as having come from here. So you see your mirror image over here, and we say it's a virtual image because it is your brain perceiving where the light rays came from. Okay, more on that later. So this is our introduction to ray diagrams, and what we're going to start with is we have a curved mirror. So let's say we have a concave mirror, and so there's going to be something over here, and an image is going to form based on the mirror, and we can draw some lines and stuff to figure out where it is, and then we can be more specific with numbers. So with a curved mirror we have a center, so call that center, and this is going to be the focal point. And the focal point ends up being half the distance of the center, or between the center and the mirror. That is the place where light rays would focus if they came in parallel. So if you were way off to the left and you were to shine a flashlight, they would all focus and focus and focus and focus. So those are for light rays that came in parallel. If it came in like this, that's a totally different situation. So to start, we draw our image, and we basically use arrows to represent these. So I'm going to draw an arrow because the arrow has a point, and that is where we say that, okay, light from the surroundings bounces off the point of the arrow and then hits the mirror, and then it's going to do certain things. So we start with, let's use red. So we start with a light ray that comes in parallel. So this thing here is called the principal axis. So that's just kind of the middle. Alright, principal axis. And a light ray that comes in parallel to the principal axis is going to, like we just learned, bounce out through the focal point and keep going. And so if you're doing these and you're using a ruler, that's a good idea. I, unfortunately, am not. Another thing that happens is a light ray from the tip of the arrow goes through the focal point and therefore will bounce out and go parallel like this. The place where those two lines cross is where the tip of the arrow for our image will be. So this is our object, this is the thing, but the image that is formed based on the mirror is this image. So to relate this to our physics girl up here, this is our object and this is her image. So the image is what we see, the object is what we're actually looking at. So here we have an object, here we have an image, and the image is upside down and it's farther away. So it turns out that if we were to sort of assign some values to this, so I just randomly wrote some numbers here, we could assume they're centimeters, which is probably what they'll be when we do something with this in class. So our object has a distance of 5, okay? D sub O, the distance to the object is 5, and that is the distance away from the mirror. Anything on this side is positive, we say. The image is, let's say, 6.5 away. And for the height, well, we don't really know, but based on these measurements, let's say the object has a height of 1. And I kind of messed up right here. This line should be a little like that, so this thing's actually a little taller, or the image. And so the height of the image, I think for this would be, and we're going to write negative 1.3. Now, the negative comes from the fact that it's upside down. It is below this principal axis. 1.3, it will be magnified. It will look bigger. When you look at this through this mirror, it's going to look bigger. And then this magnification, so here's a formula for us. M is magnification. And magnification is, we can say M equals, and it's the height of the image over the height of the object, or it's the negative of the distance of the image over the distance of the object. So you see that when we use this, we end up with a negative 1.3. So for us, our magnification ends up being negative 1.3. And if we did distance of the object, so this divided by this ends up being 1.3, and we could make a negative. Okay, so a little introduction to ray diagrams. Using and coming up with these values, we'll actually be able to calculate these. But the rules are these. So for ray diagrams, whoa, hey. Ray diagrams, in through the focal point, out parallel. So that was this, the line, the ray of light that came in through the focal point and then out parallel. And also in parallel, out through focal point. Come on. In parallel, it's been a long day. Out through the focal point. And that is this one. In parallel, out through the focal point. Okay. And we can also, well, let's just leave it at that. I've been rambling. So, next page. That page, but oh, look at all these cool examples. Okay. Concave mirror. So, same thing. Let's choose a different. Excuse me, this time the image, the object, excuse me, is a little farther away. Okay, so a ray of light comes, where's our red? Ray of light in parallel, out through the focal point. I'm trying to draw these straight. And then next, in through the focal point, so, and out parallel. Alright, decent. Hey. Alright, so this was, again, the object. And the place where our lines cross is the tip of the arrow, that is the image. And so we see two things. We see that this is closer, it's shorter, and it's inverted. This is upright, this is inverted. So let's see if we can write in some values here. Distance to the object, it looks like 1, 2, 3, 4, 5, 6, 7, 8. Distance to the image, 1, 2, 3, 4, 5. And these are both on this side, on the object side of the mirror, so they're both positive. Height of the object, let's just say that was 1, right? Kind of based, like if that's 1, that's about 1. And if that's 1, this guy's a little shorter, so let's say, I actually calculated these beforehand, so I'm going to say, let's say it's negative 0.625. Okay, looks about like that. So, magnification. Again, the magnification is height of image over height of object, or it's the negative of this over this. So we end up with a magnification of negative 0.625. So the magnification is negative because the image is down below, and it is less than 1 because the image is shorter or smaller than the object. Okay, so those are both concave mirrors. And I should mention this. These are both real images. And these are both real images because the light rays actually cross. And when we had the candle and we were focusing the light of the candle on the flash card, okay, if you got the image to appear, it had to be a real image because the light rays had to be focusing it. So let's see what happens with a convex mirror. These are kind of cool. So convex mirror, let's see. We have our focal point here, let's say, and our center here. And we need to pay attention to the other side as well, because it turns out these are going to be virtual images. So we're going to have our image, our object, excuse me, why do I keep messing this up, right here. Hey, oh great, okay. Alright, so here's our object. And we say that in parallel, so we're drawing light rays, okay, in parallel out through the focal point. So if it goes in parallel, just by looking at the mirror, it kind of makes sense that it's going to bounce off in some direction like that, right? Hopefully. So the way we are more specific about this is we're using the other focal point. So if we kind of trace this back there, all right, that's the direction in which it's actually going to bounce off. And that's the way these mirrors work. So yeah, the focal point's on the other side. The light doesn't really pass through, well, it definitely doesn't pass through the mirror, but we can use this focal point to figure out the angle at which it reflects. Okay, and then next we say if the light were to pass through to that focal point, okay, it's going to bounce off that mirror and go parallel. So we're again using, and let's see, I need a little cheater line here. If I had a ruler, I'd be stoked. So that's pretty straight, okay. So we say, oh wait, we're using red for the light. So if the light comes in towards the focal point, it's going to bounce out parallel. So notice how these light rays are getting farther apart, okay? They are said to diverge. What this means is that they're never going to cross, but if we were looking, so here's our eye. It's kind of cool the way our eyes and brains work. The brain really just makes stuff up. So the eye sees these diverging light rays and the brain thinks, oh well, because they're diverging, it must have come from over here. So, and it's just a subconscious thing. We don't even know that's what happens. Alright, so when we trace, I'm going to zoom in. Alright, we're looking at where this came from and where this one came from. And that ends up being right here. So our image, again, the image is where our brain thinks the light rays came from. So we have this convex mirror, and it looks like the light rays came from that point. So this, again, was our image over, this is our object. Why do I keep messing those up? Our object, and the image is over here. Okay, so this is a virtual image because the light rays don't actually cross, and it's up to our cool and powerful brain to perceive, I before E except after C, to perceive where the light came from. That was cool. Alright, so let's talk about these distance to the object, distance to the image, height of object, height of image, and magnification. So we knew that the distance to our object was 1, whether it's centimeters or whatever. Let's just keep this simple. So that was 1 away. The image is on the opposite side of the mirror, so it gets a negative sign, and it was not quite 1. So let's call this negative 0.8. And we'll be measuring this in the near future. The height of our object was again 1, and the height of the image, so it looks shorter than that, but it is upright, so it's positive, and our magnification would be a positive 0.8. So if we're to do height of object over height of image over height of object, we'd get this. And if we were to do the negative of this over this, we would get this as well. Okay, virtual image, convex mirror. And lastly, so one more of these. I know I've been rambling, but you're dealing with it, so good for you. So let's see, where is our focal point? We got focal points like this. I'm just making this up. Okay, it could have a different curvature, like less curvature or more curvature, and those would be in different places. And let's put our object out here. See, I got it right there. Haha. Our object out at 5. Okay, so again, this is the way it works. A light ray that comes in parallel goes out as if it came from the focal point on the other side. And then I'm going to make another little cheater line for myself. So assume this is a straight line. Who knows? Ugh, not quite. Good enough. Okay. So a light ray that goes in as if it were going towards the focal point is going to bounce out parallel. So do you see how, if we were to zoom in, right, we have, this is our perpendicular or normal to the surface. Normal, perpendicular to surface. I'm going to abbreviate that perp. So we would have our angle of incidence equal our angle of reflection. Okay. So where were we? Ah, yes. We're looking at where it looks as if these had crossed. And that would be right here. And so our image would be, our image would be right here. That's the tip of the arrow. And it is smaller, and it is virtual, and it is upright. So we're just going to make up some values here that seem appropriate. 1, 2, 3, 4, 5 as the distance to the object. Our image looks like about 1.5 away, and because it's on the opposite side of the mirror, we have a negative 1.5. The height of our object, again, we're just calling that 1. And this little guy would be, let's call it 0.3. So again, our magnification, which is height of object, height of, Dorville, height of image over height of object, or negative of distance to image over distance to object, and our magnification in this case would be 0.3. Okay, and because this is less than 1, the image is smaller than the object. Alright, so a little introduction to ray diagrams. We will be practicing, and then in the next part we actually learn how to calculate these things based on the focal length of the mirror. And we can do the same for lenses, and that's pretty cool.